basically we can extend this to now to ellipses. How? Ellipse has a bit more, let's say, what we call degrees of freedom. So do you remember in the algebraic form of the circle, we have only 4 parameters. In the algebraic form of the ellipse, you have much more. So for every one of these, you have basically a different coefficient. So right now we have 1, 2, 3, 4, 5, 6 different parameters that need to be solved. However, we can still create a linear regression, right? What needs to change here? In order to create a hyperplane that would give us with the constraint of A2 plus B2 plus C2 plus D2 plus E2 equal 1. And you have X1 and Y1 as our initial observations. What do we need to do in order to basically create a hyperplane, this time in 1, 2, 3, 4, 5 dimensions? So what if we change this Xi2 to Zi? What about Yi2 to Wi? Yeah. Xiyi to, for instance, Vi. Yeah. And then Xi and Yi stays the same, right? So you now have 1, 2, 3, 4, 5 dimensions in your data. So your matrix of your X would basically be this. First dimension is X1 with Xi2, second dimension is Yi2, third dimension is Xiyi, and then the guy. So it's the same as this, right? We have Z, which is X2 plus Y2. Why? Because we only have 4 parameters there. This one has more degrees of freedom. So we can still extend that problem, right? You have this multiple dimensions, and now you're fitting the hyperplane to 5-dimensional data. The formulation is exactly using the same function. You can actually use the exact same formulation as long as you can correct the data and put the other 3 dimensions by the X and Y. And solve it using the hyperplane, and you get the A, B, C, D, and F. So this method does not perform well, particularly in incomplete data. For instance, if you take a look at that, that is something similar to the Ellipse method, and Ellipse method is the minority state. Why is this the case? Because of our distance function. So if you take a look at different types of distance functions, the algebraic is what we just talked about. This is another type. Samson is the one that the majority of the people, for instance, Tubin or Katanagi, they use it. This is my confocal hyperbola, and this is basically the actual geometric distance. And we can see that the confocal hyperbola, if you move the point and you get the distance from the point to this ellipse, it's almost identical to basically the close to the ground truth. The Samson's pitch basically converges and has very, very little similarity, especially when you go from the point to the center. It basically gives you inaccurate results. Actually, it almost goes to infinity. Similar to if it goes, let's say, outside of it. So if it's very, very close, it gives you similar approximation, meaning that if those points are exactly on the ellipse, it gives you good approximation. If it goes farther away, it doesn't give you good approximation. My confocal hyperbola distance fit, guys. Same with if you go in this direction as well, you get basically that. Again, the Samson fit. At some point, really starts going diverging. Sorry.